Farnborough Aerodrome, June 1940. 5:42 hours. Air temperature 14 degrees Celsius. Humidity 71%. A Rolls-Royce Merlin engine roared against a dynamometer stand inside a reinforced test bay. Propeller torque measured 2,010 horsepower at 3,000 revolutions per minute. Fuel consumption 72 gallons per hour. Flame color pale blue. No detonation. No sputter. On the clipboard beside the control panel, a single notation in pencil. Fuel. Sample 12 grams. Stable to 110 octane equivalent. Below it, initials written in small precise letters, E.G.T. The exhaust fumes filled the hangar, sharp and dry. Technicians watched the pressure gauges vibrate. At high boost, where ordinary gasoline would pre-ignite, this new mixture remained calm. Compression sustained. Thrust consistent. The observers didn't cheer. They recorded numbers. Each value entered in triplicate for Air Ministry file reference F39-2. Outside, the sound reached the flight line where ground crews paused, listening. They didn't know the chemistry inside that roar. They only heard power. Imperial Chemical Industries, Northwich, Cheshire. 30 miles from Manchester. Rows of brick laboratories surrounded by gasometers and cooling towers. Smell of toluene, acetone, and rust. Inside the catalyst section, Dr. Eleanor Grace Thompson adjusted the valves on a cracking column. Age 33. Education D.Sc. University of London, 1934. Specialization, hydrocarbon catalysis and synthetic fuels. Position, Senior Research Chemist, ICI Fuel Division, 1939 to 1945. Her handwriting tight, geometric, exact. Notebook lines filled with EQUAT IONS C8H18 plus O2 CO2 plus H2O. Pressure ratios, temperature gradients, no ornament, only reactions. Britain needed octane, not theory. At the outbreak of war, the Royal Air Force faced a material crisis. The Luftwaffe's aircraft used 87 octane aviation fuel refined from continental crude. British fighters still operated on 87 as well, marginally improved to 92 with tetrathyl lead. Above 20,000 feet, under boost pressure, that fuel detonated prematurely. Engines lost power or failed outright. Every degree of detonation margin meant altitude, acceleration, survival. The United States had developed 100-octane fuel for export, but shipments were limited and dangerous under U-boat attack. Britain could not depend on imports. The Air Ministry established a classified program under the Directorate of Fuel Research, Project 235. Objective: produce 100 octane equivalent from domestic crude and coal derivatives. Eleanor Thompson became lead chemist on catalytic reforming trials. Her task: refine aromatic hydrocarbons from toluene and isooctane. Precursors using metal oxide catalysts under controlled pressure. Her workspace was not elegant. 2 bench reactors made from welded steel pipe. Heating mantles, glowing dull orange. Pressure gauges trembling at 200 psi. The room smelled of burnt paraffin. Each run consumed hours, each sample a few milliliters of liquid that might change the course of air combat. The process demanded precision. Temperature 480 degrees Celsius. Pressure 20 atmospheres. Flow rate 1 liter per hour. One error meant explosion. One correct setting meant progress. She logged every condition in graphite pencil, catalyst composition, M003, a L203 support. Ratio 1:5. Reaction yield and octane rating determined by cooperative fuel testing method CFR-F2. Result: motor octane, number 98.3. Further hydrogenation raised stability past 100%. No detonation under test pressure. The product smelled faintly of solvent and carbon. She labeled the flask synthetic, number 12G. Her discovery lay not in the raw chemistry, but in sequence. By combining catalytic reforming with controlled polymerization of olefins, she produced an aromatic-rich blend resistant to preignition. It could be synthesized from coal tar and refinery byproducts, materials Britain possessed in abundance. For the first time, homegrown 100-octane fuel became possible. The formula remained classified. Air Ministry, reference 41/3 D. Distribution restricted to 4 individuals. Thompson, Director of Fuel, Research, Liaison from Rolls-Royce, and Ministry Scientific Advisor. Under the Official Secrets Act, no one spoke of it outside the lab. Even the workers who handled drums of the new fuel never knew its composition. Labels read, Simply Aviation, Blend B. In July 1940, the Battle of Britain began. Hurricanes and Spitfires rose daily from grass airfields across southern England. Engines strained at full throttle. Fuel burned by the ton. Every gallon of 100-octane shipped from IC's Stanlow plant represented time gained in air. Pilots noticed difference without knowing why. Throttle response faster. Climb sharper. Engines no longer pinged under boost. They called it super juice. At Northwich, Thompson received fuel performance summaries through courier. Each sheet listed detonation index, knock margin, and thermal stability. Merlin engines, running on 100-octane, achieved 30% greater power output under combat boost, 1,300 horsepower versus 1,000 on 87 octane. Altitude advantage 3,000 feet. Combat turn rate improved by measurable seconds. Numbers on paper, but lives in air. She remained detached. Her reports contained no adjectives. Each improvement expressed as ratios. Pressure gain 1.18. Detonation delay 0.27 milliseconds. To her, victory existed as chemical equilibrium. The laboratories operated under continuous security. Windows covered by blackout curtains. Armed guards at gates. All male, censored. Every notebook page numbered and signed by supervisor. The work unacknowledged outside internal memos, marked secret. Success became a silence. Fuel production expanded. The Stanlow refinery converted entire units to aromatic synthesis. Toluene, distilled from coal tar at 98% purity. Hydrogen, derived from water gas. Catalysts, imported through covert routes from the United States. Output reached 4,000 tons per month by late 1940, sufficient for all fighter command operations. Each batch tested for stability, freezing point, vapor pressure. She inspected random samples personally. Specific gravity, 0.710. Flash, 0.25 degrees Celsius. Freezing point, 60 degrees Celsius. Meets requirement. The Air Ministry issued directive to all units. Use 100% octane exclusively for operational aircraft. The difference soon became history. In August 1940, RAF fighter losses fell. German formations broke sooner in dogfights. Spitfires climbed higher, turned faster, and out-accelerated the Messerschmitt Bf 109 seconds. Performance increase credited to pilot skill and airframe design. The fuel remained unmentioned. At Northwich, Thompson continued refining. Her next objective, reduce gum formation during long storage. She adjusted catalyst temperature to 490 degrees Celsius. Introduced nickel as stabilizer. Reduced olefin polymerization by 12%. Result: extended shelf life from 30 to 90 days. She documented everything. Her reports bore no name, only file code. All property of the Ministry of Aircraft Production. By the end of 1940, the process scaled across multiple plants: Billingham, Stanlow, Grangemouth. Production approached 10,000 tons monthly. Synthetic components mixed with natural gasoline from Persian and Venezuelan sources to maintain consistency. Distribution followed strict routing, sealed drums labeled aviation. Fuel 100, transported by guarded rail to southern depots. Each batch traceable to origin by batch number. Her name absent from every manifest. The war widened. Bombers crossed the Channel nightly. Fuel demand increased exponentially. Britain began blending additional aromatic compounds, xylene, cumene, to maintain octane ratings under new loads. Thompson led catalytic testing for these variants. She slept 4 hours per night, kept thermocouples running continuously. The laboratories operated under red light during raids. Shockwaves from distant bombs rattled the glassware, but the columns kept working. In 1941, the Air Ministry transferred supervision of synthetic fuel to Joint Anglo-American Committee. Her reports now carried new classification markings, Combined Chiefs of Staff Project F-101. American chemists from Standard Oil and Sunoco visited briefly, collected data, and returned across the Atlantic. Within months, similar fuel appeared in Allied supply chains labeled 130th grade aviation gasoline. No mention of origin. No acknowledgement of British catalytic method. The credit shifted quietly. She received an internal commendation, typewritten note unsigned. Production targets met. Continue experimental series on aromatic yield. No publicity, no promotion. Her salary unchanged. By 1942, improved formulations achieved 130 octane. Supercharged Merlin 61 engines adapted for these fuels reached 1,565 horsepower at altitude. Spitfire Mk9 introduced with extended range and climb. Every flight, another verification of her chemistry. Every victory, another confirmation unrecorded. She observed from distance. Graphs, not combat footage. Columns of numbers replaced headlines. Output, efficiency, energy density. One chart summarized it all. Thermal output 20,000 BTU per pound. She underlined the value once and filed it away. Inside the laboratory, the air always smelled of solvent. Pipes hissed as hydrogen flowed through catalysts. Condensate dripped into flasks. Reaction complete. Fuel formed. Her contribution invisible, molecular, permanent. By 1943, Allied fuel capacity outpaced Germany's synthetic program at Leuna and Paulitz. The war of chemistry shifted decisively. Every Spitfire, Hurricane and Lancaster ran on a blend derived from her original catalyst series. The difference measured in degrees of combustion, in seconds of engine, endurance, in the simple fact of staying aloft longer than the enemy. Thomson continued refining purity, reducing sulfur content, increasing volatility's stability under low temperature. Her 1943 report listed final parameters: research octane, number 102.8, motor octane, number 99.6, lead content, 4.2 ccs per gallon, density 0.710 grams, cm3. Results consistent. Signature E.G.T. No publication, no patent. The process classified as Crown property. By late 1944, the war's outcome became clear. Fuel output reached its peak. Britain, self-sufficient, American allies adopting similar methods. Her laboratory reduced to maintenance mode. Experiments ended. Files archived. Equipment cleaned and sealed. Catalyst vessels cooled for the last time. She signed the final logbook entry. Operation concluded. Yield satisfactory. No incident. When peace arrived in 1945, the Air Ministry declassified select sections of Project 235. Press releases credited industrial partners: Royal Dutch Shell, Anglo-Iranian, Standard Oil. Individual contributors unmentioned. She returned to academic research. Temporary appointment at University of London, Department of Chemistry. Her wartime reports locked in government archives. Years passed. New engines appeared. Jet fuels replaced high-octane gasoline. Her process outdated, absorbed into history. No citation, no recognition. Only chemical principles carried forward. And yet, in every flight of 1940, her formula had burned silently through the Merlin engines that defended Britain. Combustion precise, controlled, absolute. Her chemistry became motion. Her name remained still. Post-war Britain, 1946. Fuel laboratories fell quiet. War contracts terminated. Files sealed under 30-year classification. IC's Northwich Division reassigned personnel to civilian projects. Paints, plastics, fertilizers. The catalytic cracking towers stood idle, valves rusting under condensation. Only faint traces of solvent remained in the concrete floors. Dr. Eleanor Grace Thompson stayed 3 more months, cataloguing test data for government storage. Every report numbered, boxed, indexed. Series 12G through 15K, labeled aviation fuel, synthetic trials, restricted. Then her employment file closed. No ceremony, no summary. She moved to London. Temporary lectureship, Department of Chemistry, University College. Courses on reaction kinetics, catalysis, polymerization. Students never learned her wartime work. She never mentioned it. The Official Secrets Act remained in force until 1971. By then, memory faded, data forgotten. Yet the results persisted. Post-war civil aviation still relied on her discoveries. High-octane blending components from her catalytic process became foundations for new jet fuel standards. The Ministry of Supply requested her old data to calculate kerosene volatility for the first British jet airliner, the de Havilland Comet. Her methods adapted from aromatic gasoline to paraffinic kerosene. Reaction pathways similar: hydrocarbon reforming, hydrogenation, desulfurization, chemistry constant. Context changed. Jet fuels demanded stability at altitude and low temperature. Her synthetic compounds offered both. The same catalytic logic that once kept a Spitfire's engine from detonating now ensured a jet turbine would not stall at 30,000 feet. The molecules endured beyond the war that required them. The ministry's new fuel division absorbed her formula. Designation: hydrocarbon reformate, process number 41. The documents contained no author field. The printed covers bore the phrase developed during wartime research. No individual attribution. Ownership reverted to the Crown. Her authorship dissolved into administrative neutrality. In 1949, Standard Oil of New Jersey patented a similar process under the name platforming. Catalyst: platinum on alumina. Process conditions almost identical to Thomson's 1941 trials. The patent cited unpublished British wartime research as prior art, but the researchers remained unnamed. Recognition migrated across the Atlantic, formalized by corporate signatures. Her work survived without her. Meanwhile, Britain transitioned from piston to jet power. The Spitfire retired in 1951. The Rolls-Royce Merlin replaced by the Derwent and Nene turbojets. Octane numbers became irrelevant. Fuel quality now measured in smoke point and energy density. But the chemistry of resistance to detonation, the same stability she achieved, remained essential. Her principles evolved into Jet A1 specifications. In technical terms, her influence persisted at the molecular level. The documents describing Project 235 remained sealed. The archive held more than 12,000 pages. Test data, chromatographs, reaction logs. Each sheet a fragment of her legacy, filed under fuel research, confidential, for official use only. She never requested access. Her focus shifted to teaching, publication, quiet research on polymeric catalysts. Her career faded into academia's anonymity. The nation she helped defend remembered the machines, not the molecules. The myth of the Spitfire centered on wings, engines, and pilots. Its silent power source, rarely mentioned. The victory narrative required human courage, not chemical equations. Still, her work resonated through industry. By 1953, the British jet transport fleet consumed kerosene, produced by catalytic reforming plants, descended directly from her method. The production routes traced back to ICI's early hydrocarbon research. Her department, her columns, her data, her name absent, her influence total. In 1958, the Air Ministry commissioned a retrospective report on wartime technology transfer. The study examined cases where British research contributed to Allied industrial developments. Synthetic fuels received 2 pages. Paragraph 4 acknowledged notable early work at ICI on high-octane aromatics, identity of individual researchers unknown. She read the report in the university library and closed it quietly. No annotation, no response. The buildings at Northwich declined. By the 1960s, laboratories dismantled, tanks emptied, pipes cut for scrap. Only the foundations remained, oil-stained concrete, a few rusted bolts. The work existed now only in microfilm. The physical world moved on. In 1964, she attended a symposium at the Royal Institute of Chemistry. Topic: Advances in hydrocarbon reforming. Speakers discussed the origins of modern catalytic design. Graphs, identical to her old data, appeared on slides. The equations unchanged. No attribution. She took notes without comment. Afterward, she returned to her office, wrote a brief remark in her notebook. Repetition confirms correctness. Then she closed it. Through the 1970s, her influence continued in silence. The modern fuels that powered Concorde and the Rolls-Royce Olympus engines derived from reformate chemistry she pioneered. The parameters nearly identical: controlled hydrogenation, aromatic balance, thermal stability. Her ideas scaled to supersonic speed. No one connected the line back to 1940. In 1975, when Project 235 files were finally declassified, few noticed. Archivists transferred the documents to the National Archives, Q. The catalogue entry read, Avia 70, 312, Synthetic Aviation, Fuel, 1939 to 1945, Directorate of Fuel Research. Inside, a single folder bore the label 12G Catalyst Series. Within it, reports typed on yellowed paper. Author, line blank. Appendix contained a signature, E.G.T. Thompson. The handwriting small, mechanical, unmistakable. Researchers decades later traced her identity from that mark. One fuel chemist, cataloging the file in 2003, matched her initials to university theses from the 1930s. Her name resurfaced quietly in an academic journal footnote. Thompson's early catalytic reforming trials anticipated post-war industrial methods. No photograph accompanied it. No biography followed. She died in 1978. No obituary mentioned aviation fuel or the Battle of Britain. The university record listed emeritus lecturer, retired. Her notebooks disappeared during a departmental relocation. Only 2 pages survived. Temperature tables, catalyst ratios, yields. They ended mid-equation. Her chemistry remained alive wherever fuel met flame. Every combustion chamber carried the principle she defined: controlled reaction, maximum stability, minimum waste. Every engine ignited by aviation spirit held traces of her logic. The balance between energy and endurance that had changed the war continued unchanged. Decades after her death, restoration engineers at Duxford Museum prepared a Spitfire MKIA for flight. They analyzed residual traces in its preserved fuel system. Gas chromatography identified aromatic hydrocarbons consistent with early synthetic blends: toluene, xylene, isoparaffins. Exact match to the 12G formula from her 1940 log. 70 years later, her molecules remained. The restoration team filed their analysis in the aircraft's maintenance record. Entry: 14 billions. Original fuel composition reconstructed from May. Sample consistent with wartime synthetic source, ICI Northwich. No Chemist name recorded. Only location. In laboratories today, engineers testing sustainable aviation fuels reference the same reaction types: catalytic reforming, hydrogenation, isoparaffin blending. Modern catalysts are platinum, not molybdenum, but the equations remain hers. Hydrocarbon behavior obeys the same ratios, the same temperatures, the same mathematics of controlled energy. Technology advances, chemistry endures, history reduces invention to institutions. But every Spitfire that rose above the Channel carried her unseen work inside its tanks. Every burst of power during combat began in a reactor she once adjusted by hand. She changed nothing about appearance or structure. She changed the molecule, and that molecule changed the outcome. Archival microfilm captures her handwriting in faded graphite. Numbers precise to 1 decimal. No adjectives, no emotion, no claim. Only balance sheets of energy released and stability maintained. Her voice absent, her presence molecular. The silence of credit never disturbed her calculation. In the end, she belonged to the material she shaped: clear liquid, stable, efficient. Her existence measured in detonation margins, not recognition. The record of her life compressed into formulae: temperature 480 degrees Celsius, pressure 20 atmospheres, yield 98%. Every reaction complete, every result final. The hangars at Farnborough now serve as museum halls. Engines restored, displays polished. A Merlin test stand sits behind glass. Visitors read placards about aerodynamics and bravery. None mention chemistry. Yet the air still carries a faint scent of fuel, ghost of the molecules she built. Her story remains dispersed like vapor, invisible but persistent. The synthesis she achieved allowed combustion without destruction, power without chaos. It turned raw crude into flight. It made endurance possible. It defined victory by precision, not by noise. No one remembered her name, but her formula outlasted every aircraft she fueled. Each time an engine turned at full throttle, her work continued unseen. Every Spitfire that climbed above the Channel burned her chemistry in silence.